In a previous video, Smart Gardens 2, we saw how we could build a fully automated, self-sufficient watering system using a homemade moisture sensor and an inexpensive electric tap or solenoid as the actuator. But how well does this translate to the real world of commercial agriculture? There are many reasons why farmers want to use ag tech in this way. It can be more efficient, it makes sense in financial terms, and it also allows land to be used with less degradation. There are a variety of global needs which we face in the coming times, and you might like to pause this video to ponder the numbers shown here. Ag tech can improve productivity, which can minimise water waste and make arable land much more productive. So let's look at how one country is doing this. You're looking at Westland, a 10,000 hectare area in the Netherlands. Those whitish rectangles are greenhouses, very large greenhouses. These greenhouses provide optimal growing conditions, and note the improvements in cost, but also the efficiency of land use. In Australia, similar things are happening. Guyra Council worked cooperatively with the Costas Group to build the first major high-tech glasshouse in the north of New South Wales. Greenhouses allow the grower to optimise the growing conditions by controlling light, temperature and humidity, amongst other things. They can maintain just the right amount of water, which carries the plant nutrients. The commercial growers use sensors very similar to those that we might use in a school. In a resistive soil moisture sensor, used in a lot of schools, and the one that was used in this example, the conductivity between the probes is measured. The more water, the less resistance. But this is not as accurate as a commercial enterprise requires. A capacitor soil moisture sensor works out the time taken to charge up the sensor, and the time taken to charge is related to the soil moisture. However, there are better solutions if we're going commercial. Water in the soil will dissolve mineral salts, and this solution provides an excellent opportunity for electrolysis, eventually corroding the probe. Now, capacitor probes last longer than the resistive ones, but still only a few years, depending on soil type, and they require frequent calibration to make sure they're returning the right results. And neither of these take into account the type of soil. A sandy soil with a high moisture may block oxygen from the roots, but a similar amount of water in fine clay soil may be bound to the clay particles and not available to the plant. And commercially, it's complicated. However, the availability of water in the soil is only one part of the problem, or the solution if you like. The plant may not need water at some stages, so we'd be wasting water and energy if we just relied on soil moisture in a commercial environment. A sap flow monitor can be used to check how much water is moving in a sample plant, and a dendrometer can measure the diameter of the plant stem, indicating an uptake of water. The sap flow monitor works by heating the water carrying vessels in the plant and measuring how fast the heated water moves to the upper and lower temperature probes. The difference in arrival time can be used to measure the velocity of the water and therefore the amount of water being taken up by the plant. The dendrometer features a stainless steel band around the trunk that twists a variable resistor as the trunk expands, changing the voltage. At the Living Classroom in Bingara, northwestern New South Wales, there's a school set up that has a large variety of different sorts of gardens and different sorts of crops. We'll look here at the Mediterranean garden. And at the Mediterranean garden, certain plants have been set up to have their measurements taken. And here you can see a dendrometer being fitted to a young olive tree. A tape is used to calibrate the device. The stem is measured so that the voltage from the dendrometer can be matched to the real measurement. Now, data collection is powered by a solar panel which maintains the charge of a battery, and collected data are sent via a wireless system called LoRaWAN to an internet service provider. In this case, the ISP is Telstra, but it could be via NBN or Optus or anyone really, and could be via satellite. The internet connection allows the data to be visualized on a web server, and here you can see how, as the soil moisture drops, the plant's stem diameter decreases as well. And take a moment to look over the other measurements. Notice that the solar panel and battery are also monitored, because without them, the system can't work. The monitoring of individual plants is aided by data from a weather station, which is also connected to the web server. We can see the air temperature in degrees, reflecting the relative humidity. As the air temperature goes up, the humidity goes down, and vice versa. We can also see how much rain has fallen, both in the individual day but also cumulative over a period of time. And this can help being matched up with the water level in the soil and also the soil uptake by the plants to work for a much better management solution. So, the digital system that we developed in schools represents data by representing the moisture level as voltage. It's collected and analysed to get the cutoff point for dryness. An investigation of the behaviour of the microbit and the timing and duration of watering, dependent on soil and plant type, was carried out. We need to generate a suitable algorithm, design the code and the connectivity of the system. The production of a working model in the classroom can then be tested and then deployed to the garden. It's evaluated by observing weekly and then coming back to school to see gardens that were not dead. All done collaboratively with students from years 3 to 6 over a period of 18 months. That's not bad.